So, good day again. In the previous class, I talked about angular momentum. So today we're going to continue with angular momentum of a rigid body, like a solid object. So to find the total angular momentum of a rigid body that is rotating about an axis, about the z axis. So let's assume that a rigid body lies in the xy plane. So I said we're teaching angular momentum of rigid bodies. So to find the total angular momentum of a rigid body that is rotating about the z axis with a speed of omega, that is angular speed. So let's say this is the rigid body in the XYZ plane, Z, Y, and X. So if it's a rigid body, let's say with its center, so at there, rotating about the Z axis, like now with a speed of omega, then we can say that each particle in this body, let's imagine that, okay, a body is made of tiny particles. A rigid body is made of tiny particles. And when the body as a whole rotates, all the tiny particles in that body rotate also. And they will follow a circular path whose center, the center of that circular path is going to be the origin. Okay? The center of the circular path that every particle within this body, as it rotates, say it rotates around like that, rotating with a speed of omega, all the particles in the rigid body also rotate, okay? And they follow a circular path whose center will be the origin of this plane I drew. Now, it means at every instant, the velocity v of all the particles will be perpendicular to the position vector at every point during the rotation. The velocity of these particles will be perpendicular. That is, they're going to form a tangent, okay, that will be perpendicular to the position vector r, where this I represents the number of particles, an infinite number of particles, okay? Now, therefore, it means that since the velocities at every instant is perpendicular to the position vector, then it means that phi equals 90 degrees. So it then means that a particle of mass, let's say for a particle of mass mi at distance ri from the origin has a speed of v equals omega r, which is the speed that relates angular velocity to the linear velocity. Okay, so from the previous formula of angular momentum, that we saw earlier, of L equals mass times omega times r, the position vector, then from this formula, L equals mvr, then it means we can substitute, we can put this formula here, V equals omega r, V equals omega r into this particular equation here. So it becomes L equals m omega r times r. Okay, so this becomes L equals m omega r squared, because these r's multiply each other out. So we can just apply our I there. I just represents an infinite number of particles, because we're looking at the angular momentum, the total angular momentum of all the particles in within a rigid body. Okay, so it then means that in total, if we're looking at the total angular momentum of the particles within a rigid body, then we can just say the summation of all of the total angular momentum is equal to the summation of m, then let's put the r square inside now, times omega. And we know that this m r square omega is equal to this here, mr squared is equal to I, where I is the moment of inertia. The moment of inertia, I is a moment of inertia. Sorry, of inertia. Okay. So the formula, the final formula becomes summation Li equals to summation Li equals I omega, because we're substituting this into this equation, mr square equals to I. So now the equation becomes Li, I equals to IW. So this is the formula for total angular momentum of a rigid body. Total angular momentum of a rigid body. So let's look at an example. Let's take an example. So the question says, sorry. Okay. A turbine fan in a jet engine has a moment of inertia of 2.5 kilogram meter squared. About its axis of rotation. As the turbine starts up, its angular velocity is given by omega z, which is equal to 40 radians per second squared times t multiplied by time squared. A, find the fan's angular momentum. Find the fan's angular momentum as a function, angular momentum as a function of time and find its value at time equals 3 seconds. That's question A. Question B, find the net torque. Find the net torque on the fan as a function of time and find its value at time equals 3 seconds. So don't have much space to write on, but I will try. So solution to solve this. So the first question says we should find the fan's angular momentum. And remember earlier we saw that angular momentum L is equal to I omega, right? I omega, where I mentioned is the inertia, okay? Is the moment of inertia. So in this question, we're asked to find the angular momentum, and we're given omega, the angular velocity, as 40 rads per second square t squared. And also, we're given the moment of inertia, I, as 2.5 kilogram meter squared. So we can just substitute this into the formula. So L is equal to 2.5 kilogram meter squared times 40 rads per second square, then the t squared there. So this gives us 2.5 times 40 gives us 100. Okay, 100. Now all these units, we need to take care of all these units. So it's going to become 100 kilogram meter squared per second cube. Okay, so meter squared per second cube. All right, now remember there's a t squared outside, so times t squared. Now the question then says that at time equals 3 seconds. So we are going to substitute, say, find its value at time t equals 3 seconds. So we're going to put that value here, value of t equals to 3. We're going to put it into this answer here so that we can calculate the angular momentum at that time. So it then becomes, I have to erase this part. So we're then going to have 100 kilogram meters squared per second cube times 3 squared times 3 squared, which is 9. So this will give us 900 kilogram meters squared per second. Now, the reason is because the reason it is per second is because the time t squared, this time t squared, the unit is going to be in second square. So this and previously we had a second cube here, second raised to power 3. So by the time they divide each other, we're going to be left with 1 second left. I don't know if you get it. What I mean is here we have s raised to power 3, and this the unit of this time t equals we had time raised to power 2, which means the unit of time there is going to be second square. So by the time the second square cancels the second cube, we're going to be left with just 1s. That's why the formula, the final formula becomes this. Okay, so that is that on part A of the question. So the part B says we should find the net torque. We should calculate the net torque on the fan as a function of time and find its value also at time t equals 3 seconds. So what is the formula for torque? Excuse me. So we know that torque as a function of time is equal to dl dt. Okay, so it means that dl dt, so therefore dl dt is equal to the 100 kilogram meters squared per second cube t squared. If you are confused, you can go back to the L we got, the initial for the question A, we got our initial our angular velocity L as 100 kilogram meter squared per second cube. We got that earlier, so that's what I'm using here. So we're going to differentiate this, differentiating this with respect to time. You notice it's t squared here. So this, all of this will not be affected, but this time will be affected. So it's actually going to become 100 kilogram meter squared per second cube times 2t, where you differentiate t squared with respect to time. It becomes 2t. So this is the value of the net torque. This is the function that we're going to, this is the net torque with function of, this is the net torque on the fan as a function of time. Now, to get its actual value at t equals to 3, all we just need to do is substitute t equals 3 into this expression here that we got after differentiating. So it now becomes 100 kilogram meter squared per s cube times 2 times 3. Okay, since time is 3. So this is 6. 2 times 3 is 6. 6 times 100 is 600. So the final answer is 600. Okay, so the unit for torque is Newton meter. So that is 600 Newton meter. So that will be the answer for the net torque. So I hope this helps. We're going to see you in the next video.